Hello, good afternoon. I would like to start our colloquium. Today I am honored to introduce our speaker, Professor Merav Opher. She is in the astronomy department at Boston University. Her research is focusing on understanding the heliosphere. She'll tell you what it is in a couple of minutes, how it evolved through the history of the sun, how it might or might not contribute to emergence of life on Earth. Big issues. She has been awarded numerous accolades. She's a Radcliffe Fellow from the Harvard Radcliffe Institute. She earned the Presidential Early Career Award. She was selected as a Fellow of the American Geophysical Union, the Simon Guggenheim Fellow, and a lot of other things. She is currently the director of SHIELD, which is one of the biggest NASA theory centers focusing on space physics, space research. And today she will tell you about the effect of the sun's trajectory through the galaxy on Earth's climate over the past 10 million years.
Thank you, Mihaly. You can hear me. Good. For the nice introduction. Yeah, light would be good. I'm not going to talk about SHIELD today, but if you are interested, you can ask me questions. It's really exciting endeavor, SHIELD as a center. So this topic that I'm going to tell you about, I started thinking a couple of years ago when, as Mihaly was mentioning, I was a Radcliffe Fellow, and I was decided I had a year to think out of the box and move from heliosphere and think in a bigger picture other effects of the fact that we have a heliosphere. So I'm going to start introducing this idea that you probably know, but I just wanted to peep that for the physicists in the audience, not astronomers. And please, if I go into jargon or I go something obscure, raise your hand, ask me a question, okay? I hate jargon, so I'm going to try not to talk with jargon, but please stop me. So anyway, I like to say that if you're a physicist or somebody not working in astronomy and you're looking at stars, you don't realize that they're surrounded by a home. They move. They're not just naked structures, but they're surrounded by bubbles formed by their winds. So stars have winds. They move through the interstellar medium, and that wind get deflected. So that get deflected around them by this motion. And can you hear me? I can go like this. And you can hear in the back. Good. And that create, those are images of astrospheres. It's really tough to measure astrospheres because in general, stellar winds are not very dense or rarefied. So it's almost like a transparent cloth. And sometimes you only see the shock in front of this bubble. But in any case, we know that stars have bubbles. We call them astrospheres. And our own sun, Helio, has heliosphere, right? And what it's nice to call attention for, and I don't have the answer in this talk, I'm just calling attention to it, that of course we have life. And so we have a habitable astrosphere. And I'm calling attention to it because that was what set me into this journey thinking is, does the astrosphere or the heliosphere has anything to do with how life originated or evolved on Earth? I don't have the answer yet, but I do have some consequences that probably affected the existence of heliosphere affected what we know today. So we created this movie for the SHIELD enterprise, and it shows Earth and all the planets sitting within our heliosphere. This is one representation of the heliosphere. It's one that my group likes, the cosine heliosphere. Still being debated, the shape of it, but we know it's engulf all the planets. So it's huge. It's, if you are an astronomer and you're used to astronomical units, the size between, the distance between us and the sun is 1 astronomical unit. The size of this bubble is 200, at least in the nose. It's big. One thing we do know that the heliosphere does stop galactic cosmic rays or the low energy galactic cosmic rays. So we do have these beautiful measurements by Voyager spacecraft that were launched, Voyager 1 and 2 in the 70s, and they measured the intensity of the galactic cosmic rays as they started going out of the heliosphere. So they went through the nose, and this was well inside the heliosphere, and the intensity varied. This is due to the fact that the solar wind vary with the solar cycle, but as they got to the edge of the heliosphere, the intensity went way up, and went way up by 70%. And the measurements in the interstellar medium, this is galactic cosmic rays up to 1 GeV. The heliosphere is a really good shield, hence the name of my center, SHIELD. So that was because they really do affect this low energy galactic cosmic rays. We don't really understand this jump. This is one of the big issues. Why the heliosphere shields 70%, and how it varies with time. But we do have these measurements. And because we have dust people in the audience here, I also wanted to say that I'm not going to talk much about it in this talk, but we also have measurements by Ulysses of interstellar dust well inside the heliosphere. And we know that is not the distribution of dust in the interstellar medium. So we know that the heliosphere affects the entry of dust as well. Yes?
Can you say, what is the like a density profile, radial profile? Like, is it more like a cloud, or is it more like a shell?
Of what? Of the heliosheath?
Yeah.
Or the heliosphere? The heliosphere is very, I'm wondering if I have a diagram that I can show you later. Okay, I will wave my hands and tell you. From the sun to the edge, so before you come to the last piece, when the solar wind gets compressed, it's very rarefied, the solar wind. It's falling 1/r², the density. Then it gets compressed by a loud shock, the termination shock, the density go up, not by a lot. This is a weak shock, 2.5. So the density is a little more compressed. And then it's go by a factor of 10 to the interstellar medium. Okay, so the sun, this beginning of this story that I want to tell you, comes into talking about the motion of the sun. So the sun moves actually around the same speed as the Voyager spacecraft left the solar system. It's moved with 19 kilometers per second, or 19 parsecs. Again, this is units in astronomy, big, much bigger than AU, parsec per million years. And I like this unit because this 19 parsec per million years give you an idea how fast this is. So the sun is here. This is a motion of the sun. There is lots of clouds. The medium outside the heliosphere, as you probably heard by talks here, is not homogeneous, has lots of little clouds. And right now we are sitting in a warm interstellar medium that have a hydrogen density. It's partially ionized. Hydrogen density of 0.1 hydrogen per centimeter cube. And those little clouds here are sizes of parsecs, maybe 15 parsecs, this whole region. So within 1 million years, this is a blip in the age of the sun, we are out of this region. So when I started putting these numbers, I started thinking where the sun was if I start going back in time, or where the sun will be if I move forward in time. Okay, so one of the things we do know, and this is again work that Jeff Linsky and Seth Redfield did, they map all these clouds outside our heliosphere. And this is a 15 parsec region. Within 1 million years, we are out of that region. where we are. Right now, we are sitting within this ginormous structure called a local bubble. It's 100 to 200 parsecs now in diameter. And this was formed probably by many, there are models that try to explain the structure, by explosions of what we call supernova. So when a massive star dies, it's explode, become a supernova, and it drive a big shell. This probably was a result of many explosions of supernova and form this expanding thing. It's not static, it's expanding. And sometime in the past, we entered into this structure. This is where we are. So we will come back to it in a minute. But one of the good coincidence when I started thinking about it and started talking across the river from BU with the Harvard folks that do this type of work, they pointed out to me the big revolution we are having with the Gaia instrument in mapping the structures around the sun. So this is a slide I stole from Catherine Zucker, where she showed in different studies the sun's trajectory of what we know about the size. This is around, we are talking here kiloparsec, but this is what we know from the galactic neighborhood just a couple of years ago, 2018. Gaia instrument, one of the big problems in astronomy for the physicist is distance, to know where structures are, how far they are. And Gaia used parallax to map them, so we are able now to, this is the same field of view now in 2024, and you can map much more accurately the structures. So now we can start thinking where the sun was, which structures it encountered. So you need to know the distance, and you need also to know the relative motion between the sun and those structures. So I'm going to tell you a story that shows you that we think that in the past the sun encountered massive clouds, much more massive than what our neighborhood today. So our neighborhood has densities of 0.1 particles per centimeter cube. We think that in the past we could have encountered dense clouds of density 3,000 particles per centimeter cube. So 4 orders of magnitude denser. And the effect of it is that this is a heliosphere of today, in that movie I showed you. So this is a view from outside looking into the sun. And like I said, the size is around 300 astronomical units. So the sun, Earth, planets are all inside. But if you encounter something that has a much stronger pressure, it's going to compress the heliosphere. The size of the heliosphere is balanced by the pressure of the wind and the pressure coming from outside. So if you are in an environment way denser, way stronger pressure, I'm going to tell you a story that shows you that there were moments where the heliosphere shown here in yellow were way inside the trajectory of Earth that is 1 AU. So Earth was unprotected. We were expelled from our home. So get out. At least for part of the trajectory, we were out. And I wanted to give a historical perspective. I'm not the first one to think about it. What will happen if the sun encountered massive clouds? And there is lots of work that thought about it. There are works going back to the 70s. There was a fury of works in the 70s by Talbot and Newman, and later in the 80s, arguing that if the sun would encounter dense clouds, and they were thinking the same type of densities, 3,000, 1,000 particles per centimeter cube, maybe the solar wind will shut off. So if you ask me a question at the end, I can talk about this. But they were thinking the sun won't be able even to drive a wind. There are other work, and we have in the audience Begelman here with Martin Rees in the 70s, And again, Talbot and McKay trying to figure out if such encounters would have affected the climate, and arguing that Earth probably would have affected if the sun would have encountered such clouds. There is other works by Pavlov. He has 2 works that argue that you can even have a snowball glaciation. And this Yabushit and Allen even went further. You can have a biomass extinction. So I started thinking about this project because I saw this plot, actually. It was in a fall AGU. I saw this plot. I was like, that is very interesting. They have detected iron-60. Iron-60 is produced by massive stars that dies and create the supernova that I told you about, and they expel iron-60 into the interstellar medium. And this series of works, this is a plot from 2021 by Warner, showed an increase in iron-60. It's a very hard measurement to make. And they made it, and they show an increase in the abundance of iron-60 detected everywhere. This was a global phenomenon. They detected in several ocean samples, they detected in Antarctica snow, in the moon, on the moon, in lunar samples, and also in galactic cosmic rays measurements, 2 peaks. One, if you look at the time, between 2 to 3 million years, and 6 to 7 million years. So something happened that brought iron-60 to Earth. And the suggested scenario when this was first presented was that this was because there was a supernova exploding. And it's the most natural thing because supernova produced iron-60. So you would think, okay, a supernova exploded. And that was started by Brian Fields. He has a series of papers started in 2008. And there are a couple of challenges with that. One of them that you have to have 2 supernovas, 3 and 7, because you don't have this increase otherwise. You don't, it's not a continuous. So you have to have some fine tuning here. You cannot explode them too close, less than 8 parsecs, because if not, you really kill any life. This was shown by this work. So you have to explode them in the right time and a little bit farther out. And then you have the problem, and we can discuss it later, how to bring iron-60. So one of the big challenges we see in that you need to have 2 iron-60. And when you look at what produced that big structure I just showed you, it's several supernovas that exploded far away. So why 2 in our neighborhoods? And not what we have to produce a local bubble. So we thought in a different scenario that I will tell you, cold cloud scenario, thinking that the sun encountered massive structure doing this 2 times. And we went, and what I wanted to do when I started thinking about it is, can I use the most modern astronomical data and pinpoint the crossings? That will not be, oh, maybe we found cold cloud, but can I say which cold clouds? This turned out to be much more complicated than I thought when I started. Cold clouds are really hard to detect. But I will tell you 2 instances we think we did pin down. So the idea that if you have a scenario where the sun encountered a cold cloud, you can have supernova exploding far away. They will enrich iron-60 into the interstellar medium in the dust that get incorporated into this massive cloud. So you don't need any more fine-tuning on the time or the distance. They're there in the cold cloud. Okay. So before I go to the story, there is another piece that I will tell you. Yes?
Is iron isotope also correlated to plutonium isotope?
Plutonium is a much harder, but yes. It's a much, the error bars are much bigger.
What's the source of that? Is it?
They also think it's supernova. Yeah. Oh,
Didn't all of the iron isotopes come from supernova? What's special about these?
yes. No, so the question is, yes, they all come from supernova. Why suddenly at 2 to 3 million or 6 to 7 we see an increase in abundance? That's the question.
So why would it be different than just the iron that's already here?
Because you see a increase. You do see, I'm not showing here a data that see some flux of iron 60s that come in continuously, but these measurements should see an increase in that abundance. Okay. One other piece that I will tie together at the end of the talk is effects on climate on Earth. And these pictures I took when I visited a friend of mine in the Lamont in Columbia University, when she showed me how you learn about the climate in deep ocean samples. So those are, you learn from the past temperature on Earth from these shells called foraminiferas. And you can know by the number of little rooms that they make the age of these foraminiferas. And I love it. As they age, they build more houses. So you can date these shells, they scoop it from the deep ocean, and they can filter it, and they know the age, the dating, based on the number of rooms that these shells have. What they also do from the foraminiferas, they take the ratio of oxygen, O18 to O16. This is a very sensitive ratio to temperature. So they can relate that temperature, benthic, the deep ocean, to the temperature in the ocean. And then they have proxies to convert the deep ocean to the surface temperature. But the way we know about the history of the temperature on Earth, the cute part, the 60 million years, is what we have from Gaia now. This is a field of view, 1 kiloparsec, that we know where the sun was, is what we know in the deep ocean. Isn't cool? So we know the history of Earth, the temperature of Earth, going back 60 million based on the foraminiferas. And the temperature varied. Okay. One of the things when I started reading the literature that people in climate knows, for me was news, I was learning, is that when you include astronomical effects on climate on Earth, what people that do climate, they include the fact that the axis of Earth change with time. So you have a variation in eccentricity and variation on the other parameters of the Earth axis that are shown here. Those are called the Milankovitch cycle. The beauty of that is model this variation on 10,000 years. You can go down to this O18 ratio in the benthic, the foraminifera, and you can see this beating. Today I talked to students doing clocks. I know there is lots of people here working atomic clocks. Look at this clock. Isn't cool? So you go to the deep ocean and you know that the axis of Earth varied. I found it just so cool. Anyway, you see these variations, but climate people will only include the variation of the axis. There is no conversation where the sun was. It's not an external forcing at all in the climate models. One thing that is interesting, if you look at the most recent reconstruction of the deep temperature, this comes from Westerhold 2020. They do show that there were times, not just only you can map the temperature, the history of Earth varying 60 million going back to today, and was hotter before, became cooler, but there are transitions that happen every couple of million years that are not well explained. So we are raising a possibility, we're just the beginning of this research, that perhaps some external forcing, like the position of the sun, provoked some of this transition. I know it's a bold idea, and we're taking baby steps to see if it's true, but I just wanted to show you. Okay, so, never, no, what? I really don't know all the details. I know that O18 it's related with the mass, but I don't know the exact details. They seem that this is very well calibrated, that I know. Yeah.
I learned
But
about this in an oceanography class, and it is just isotopic kinetics. Like the lighter isotopes evaporate more easily, but at higher temperatures, that doesn't matter so much.
So is this in the atmosphere or in the ocean itself?
I think
it's
ratio in the ocean.
it's in the ocean.
Yeah.
Right, it's in the ocean, right. I think my understanding that the translation from the deep ocean temperature to the surface is they're much more model, they are more problematic, but the deep ocean, I think it's so probably. Okay, so this paper has a funny story. So I started thinking what happened 2 to 3 million years ago. I'm a heliospheric scientist. I did my PhD in astronomy a long time ago. And I just opened the literature and tried to find a cold cloud. Was there any cold cloud in the direction where the sun went? And I thought I found, and I thought was this structure here, because I saw in the literature that there is this big local ribbon of cold clouds. And I wrote a paper, and we put it in the archive, and I gave a talk. And then I get a phone call from Josh Peak. He is a world expert of cold clouds. And he said, I am not sure if it's that structure. And I said, please calculate, prove me wrong. I really would like to know. I'm making a guess that is there. He got sick with COVID and spent a whole week making calculation. Was great. I was in a conference with Lisa Goodman that does interstellar medium, and I get a phone call from him, and I was like, oh, I will have to retrieve the paper. It's probably wrong. He said, Merav, you were right, but it's not in the point where you thought, it's to the edge of the structure. So I actually did pull out the paper, and I said, I'm rewriting it with you as a co-author, and we're going to say where it is. So that is this paper. Took us 2 years with this, me adding Josh Peak and his calculations. And we think that 2 to 3 million years ago, there is a possibility we intersected the edge of this structure. So originally, I thought was more to the center. And Josh's calculation, what he did, he had a paper back in 2011 working on it. And Hod was the one that discovered this big structure, the local ribbon of cold clouds. We do not know the origin of this structure. But they're very rare cold clouds. But the biggest piece of this structure is called the local Leo of cold cloud. That was studied in details by Mayer et al., and they got a density really high, 3,000. It's cold. It's one of a massive cold cloud. It's a very placid structure. So we are assuming in this paper, and we have all the arguments by Josh Peak, that because it's so placid, probably the different members also have very massive density. So we did calculate the relative speed of the sun with the motion. We assumed that this structure, because we don't know how it's evolved in time, so we assumed that it's moving with one single velocity. And Josh, using his different techniques, derived the 3D speed of this structure. Hi, friend. And we compared the relative speed between the sun and this structure, and we argue that within 1 sigma, we went through the tail end. I do have Monte Carlo simulations that show our variations. If you vary, we don't know the exact distance of this structure, so we vary the distance and all the parameters. Within 2 to 3 million, we cross that structure and the tail end. So this is just the details of it. You can look on this paper more, but this is a relative. That is very well known. The relative speed, 14 kilometers, not really fast. So it's, again, between 14 parsec per million years. We're moving through this structure. What is uncertain is how far this is. So we put the error bars on that, and we get this 1 sigma crossing. And what I end up, this is actually what Josh took from the Galfa H1 survey. This is a tail end of the local ribbon of cold clouds. So this will be one of these clouds that we crossed, and he named it local Linux because it's in the direction of the Linux constellation. So there is a possibility that we cross that. And I end up just using my dandy MHD simulations that I've been using forever. But now instead of using, this should be centimeters, 0.1 particles per centimeter cube, this is our environment right now, I cranked up the density for 3,000. The temperature really doesn't matter, because really what the pressure that is going to make is an interaction between this hydrogen and the ions. So I will show you in a second. So I crank that density, I put that relative speed, and what I got, that the heliosphere collapsed. And here is a side view of the heliosphere. The sun is here. This is a supersonic solar wind. I didn't say it for the physicist. The sun drives a supersonic wind that goes through a shock. I think you were asking me the density. It's a very fast wind that goes through a shock, and now the shock is much closer to the sun. Look at the scale. We are talking now 0.2 astronomical unit. We just collapsed the whole thing. The other very interesting thing, and this is what got me thinking about the climate effects, is a hydrogen. Hydrogen atoms, they do this process, you probably heard it, of charge exchange. They exchange charges with the ions, and the mean free path of that process depend on the hydrogen density. For this very, very massive cloud, the mean free path becomes so small that the hydrogen get basically stopped at the heliopause. And because of gravity, it increases. So you have a really high density. Look at this. It's get to 40,000 here. But even if you put here at the nose, is really massive hydrogen. Now think about Earth. Earth, in this type of scenario, this is a view, this is a rotation axis of the sun. So this is where all the planets are. And this is Earth in and out the heliosphere. This is a top view along the rotation axis of the sun. Earth was expelled from its home. It's in the interstellar medium, exposed to massive amounts of hydrogen, increased radiation, remember, not blocked by the heliosphere, and for some time is inside the heliosphere. Okay, so we created a cute movie that shows the heliosphere of today with the sun and Earth. And as we're crossing through the cold cloud, the charge exchange pressure pushed the heliosphere back. If you ask me later, I can tell you why it's long comet and not a core sun. But the Earth is out for part of the trajectory, and here we just showed more radiation. This type of, if I just play it again, this will happen as we are crossing through the cloud. As soon as we finish the crossing, the heliosphere will come back protecting Earth. So it's a limited time that depends on the size of the cloud. So that was exciting. And then I gave this talk in Radcliffe as I finished my fellowship. And Alyssa Goodman was at the audience. And she's like, what about 7 million, the second peak? And I said, local bubble, right? Because I just did a back of the envelope calculation. 7 times the velocity of the sun, we get 100 parsec. So she said, okay, great, let's model it. So she put Catherine Zucker and her team, and they had a beautiful paper on the local bubble in 2022. One of the beauty of this paper, that they showed that the edge of the bubble is filled with star-forming regions. And star-forming regions are cold and massive. So it also brings the possibility that edges of supernova bubbles can harbor massive clouds. Okay? I have just already to tell you that in the direction where the sun crosses a local bubble, there is no visible cold cloud right now. Those clouds evolve within million years. So it could be that it was there, moved, or dissipated. So what we did, I am not showing all the details here, but we could derive, that is a precise derivation, our relative speed. So we have the expansion of the cloud, of the local bubble, our relative speed, it's much faster, 36 parsec per million years. And I assumed a density of 900. And in this case, when it's not that dramatic of a density, I get it collapse within Earth's trajectory. And again, because our relative motion is in that plane, if you look at the geometry, this is the rotation axis of the sun. Earth is in and out this way from the heliosphere. What it shows, this type of simulation, that is not just the speed, the density, but the geometry will matter for the Earth effects, because it will matter how much time we spend inside Earth. We made lots of arguments in the paper that we can even go down to densities of 280, still compress the heliosphere. And this is seen if you include some turbulent motion in the shock, you could go to this lower density. So we argued here that here we can see a cold cloud. We think it's a local ribbon of cold cloud. Here we are arguing that because the edge of the local bubble have massive clouds, that there was a cloud along the trajectory of the sun that collapsed. This actually should be inverted. This was a case in 2 to 3 million years, and this is 6 to 7. Question? Yeah.
Yeah, how sharply delineated are these clouds? In other words, how long would it take from getting outside the cloud into kind of the really dense region?
I am getting to it in 2 slides. That's great. And ask me if I don't touch sufficiently. One of the things I started thinking is the frequency of that. If you go back to old estimates, they used, the distribution of clouds, and they said we will get every gigayear. Those are the old estimates. We are revisiting those estimates now, and at least what we are finding that it could be much more frequent. I cannot give you the number now. We are revisiting it with Catherine Zucker and her student, looking at simulations of stars moving in the galaxy. We are also looking at data to see if we can do a statistical study how often we have a chance to encounter cold clouds. My just suggestion here that we got 2 to 3, 6 to 7. There's another paper by Marconi and João Alves said, arguing that at around 13 million we encounter another cold cloud. So if it's true, they're based on observations here, it could be that the cadence is much more frequent. Okay, the duration depends on the size of this cloud. And bottom line, we don't know the size. When you look at the local LEO of cold cloud, this is one cold cloud, they can only measure one of the diameters of the cloud. The word is escaping me. The other line of sight, we don't know. So there is, at least in one aspect ratio was 200 AU. But the idea is, this is Josh's argument, that clouds are parsec size, and he has a new observation in 2025 using echoes. This is a beautiful technique that they went to one of cold clouds and showed that they are actually filamentary. So my feeling is that they're probably very thin, very elongated, and probably have way more structure in it. Okay. So here we are going to the most speculative piece. We are trying to figure out terrestrial effects, but we are trying to do it as quantitative as we can. So the two aspects I was interested in exploring is increased hydrogen that I see by the simulation, an enormous increase of hydrogen. I'm going to argue that there is an increase of radiation, not just because you have more galactic cosmic rays because you're outside the heliosphere, but even when you're inside the heliosphere, you have more energetic particles. So Earth is going to be bombarded by increased radiation, and sometimes when it's out of the heliosphere, increased hydrogen. Okay, so going back to classic works, there is a work by Mihaly and Thomas that I mentioned earlier that tried to see what will happen if we encounter 1,000 particles per centimeter cube cold cloud. They did some chemistry study, and they argue that Earth is going to be covered by mesospheric ice clouds that will be global and will trigger a cooling of the surface and will trigger an ice age. They included a hydrogen coming from the increased density. So for the climate folks, 570 ppm on top, and have a whole chemistry arguing that it's going to deplete the ozone and create these ice clouds. So I managed to convince Jess, that was working supernova, to join my group. I sent it to here, to Boulder, to learn Wacom. I was like, let's do climate. Let's do climate models and see, can we redo those simulations and see the effects? So here I am trying to learn climate as we speak. So we published in GRL a paper in last year where we used a 2D, a simpler one, because we wanted just to get our feet wet. And we used a 2D Goddard climate model. And what Jess showed, that the ozone with this increased hydrogen, like what Mihaly and Thomas argued, the ozone is depleted completely in the mesosphere, like 90% gone. And there are formation of cold clouds in the mesosphere. What he found, that they're seasonal, they're not global, and they are at the poles. But then I said, okay, great. There was a very slight increase in the stratospheric ozone. So our next step, and this we've been working for the last 2 years, so you have to be patient. We don't have results yet, because we're still going very careful on that. How these mesospheric effects get transported down. And Wacom is way more complicated than my MHD code, so we're going really slow on that. One of the things that this is just preliminary, just to get your taste what we're trying to figure out, that if you have a lot of water in the mesosphere, we are working with climate folks that are helping us. If you have a very strong polar vortex, that is one of the biggest ways that you bring stuff from the mesosphere down. So this is a control run that Jess ran. This is showing just 70 to 90 degrees in the north. And now when he increased all the water, he can see water vapor going down to the stratosphere. But that is with a run with a very strong polar vortex. So we're still in the baby steps. I just want to show you where we're heading to see, to try to characterize the climate effect. There's another aspect that is really interesting. Apparently our papers also provoked people that do cosmogenic to start looking for signatures. And so there is a couple of series of papers last year, one from Noll et al. And one from Polyanov, trying to look in beryllium-10 if there was a crossing of cold cloud. If you have an increase of radiation, you can produce more cosmogenics. And I will show you, one of my students is looking into it. I will show you some results on that. And he argued that around 10 million we cross a cold cloud. Yes, question?
What is cosmogenics?
Are those 10, like beryllium-10 or aluminium 26? And they have long lifetime, not half long, of million years, so you can start seeing changes on it. So Knoll argued that in iron manganese crust, you can see a peak on beryllium-10. And this is not explained by terrestrial effects. So he argued that you barely see anything, 2 to 3, 6 to 7, but you do see a 10. My collaborator that does beryllium-10 is arguing with me that beryllium-10 is really complicated around this time because the variation in beryllium-10 in iron magnesium crust, this is all terrestrial effects. It's how beryllium-10 is produced in the atmosphere, get mixed in the ocean. So it's really hard to pull out signatures here. So this is iron, magnesium. She's trying to look in marine sediments that are a little bit more precise to find it. So I'll come back to it in a second. Before I tell you about the beryllium-10, we talked about galactic cosmic rays being, the radiation being much stronger. Let me tell you the piece about the radiation inside. So Earth is going outside and in the heliosphere and its trajectory during these collapsed periods. One of the things that occurred to me was, look at the termination shock. This is a shock that slowed down the supersonic solar wind. Currently, the termination shock is weak. Is, like I said, beginning of my talk, is a shock of a ratio 2.5. This has to do because processes that make the hydrogen come into the solar wind and get assimilated in the solar wind and weaken the shock. What will happen when the neutrals don't come in? When you have so much neutrals that you don't have charge exchange inside the solar wind, suddenly you will have a strong shock. So I started thinking that a closed-in shock, for the shock aficionados, it's not a perpendicular shock, it's a parallel shock, but it's a strong shock. So I gave results of my MHD simulation for this closed-in termination shock to a guy in my SHIELD center that I pull into this collaboration and say, can you calculate for me how much the solar wind particles are going to be accelerated? So he used shock. If you do shock physics, you know you need to do kinetic. You need to do hybrid codes to really get the particle spectrum. So he did a hybrid simulation for me, and this is a result. This is just to show that the method we are using to produce a particle is solid. It's something that he has done for all the shocks measured by Parker Solar Probe, by other instruments in the solar wind. We know what we're doing in shock physics. And what he gets, this is a spectrum he gets. This is a galactic cosmic rays, it's MEV. This is outside the heliosphere, the black. This is inside the heliosphere. The blue is what we get from a closed-in termination shock. And it's orders of magnitude higher than the largest solar energetic event, the Halloween storm. Remember those Halloween, if you know, Halloween storms, solar energetic events are days. This is not going to be days. This is going to be months because it's doing the termination shock closed in. So Earth is zooming in the heliosphere here, getting zapped by these energetic particles. And we call them HEPs, heliospheric energetic particles. So Earth is going to go inside, getting a lot of radiation, and then it's going to poke his head outside the heliosphere and get lots of hydrogen, not a lot of radiation. So the environment is going to be interesting. And yes?
It has its own magnetopause, right?
That is I did not include the magnetosphere here. I have heliopause, not a magnetosphere.
Yeah, but because it has magnetopause, it should shield some of its effects.
Exactly. So that is, we have a whole discussion about that. This is another topic I'm not even going to go. We know that the particles are going to come from the poles if you have a dipole. So over the poles, you will have this radiation no matter what. There is also a possibility that during periods, like around 2.7 million years, there is reversals of the Earth magnetic field when the magnetic field goes really low. We explored both regimes. Okay, so what we did for beryllium-10 was to use an atmospheric model, state-of-the-art atmospheric model, that creates beryllium-10. I wanted to see how much beryllium-10 is produced by this radiation. And so my student Ananika did that, and she did it for different crossings, because we don't know the size of the cloud. So they did it for 100 years crossing to go to 1 million years. And what she found that she included the time resolution that you can measure that, both in ocean sediments or iron magnesium. What she found that if you just account for galactic cosmic rays, it's really tough to pull out the signal. You can, if the crossing is really long, it's above the error bars, that is a factor of 2 of variability. But the cloud needs to be big. The cloud needs to be parsecs. If it's AU or 100 AU, you won't see it. So it's possible that when I go back to the null, if this is still valid, it's possible that this signal is so small here because the clouds are small. This is something that we need to revisit with marine sediments that are more precise. She also did it for including those energetic particles accelerated in the termination shock, and the signal is much stronger. Again, you have to pull it out, this signal, if you have a large cloud. For small clouds, you won't see. And I'm seeing that I'm talking too much, so I have my conclusion. So the intensity really will depend on the size of the clouds. The bottom line that the clouds needs to be big for you to pull out the signal. So we are advocating for new high-resolution measurements of this beryllium-10 so we can pull out that signal. And I think more to come to see the climate effects of such crossings. That's it. Ethan.
With Anna's beryllium-10 production work, what sets the width of that enhancement? We saw the enhancement in beryllium-10. What sets the width of that?
The width is just a crossing. She's just integrated. She's zapping the atmosphere with radiation, and she's integrating the signal. Just that.
So the half-life of iron-60 is 2.5
yeah.
billion years. So how does this factor in this whole model? So in particular about, the timing of the supernova. Because this also puts, constraints on the potential different distance of the supernova.
Right. So Jess Miller, that is an expert on that, had a whole calculation in my second paper, the 2024, including that. So all these factors you're mentioning, them will enter in the width of the peak that I didn't talk here, because you will have the increase, but also why it's wider, why it's thicker. So he included all these factors. If he included the ratio of the explosion of supernova that explained the local bubble, the distance between each explosions, the fluency, there is some debate about it, but the fluency, how much the supernova put the iron-60, and he integrated it. He could explain the width. There are some wiggles room here, but yeah.
How much stronger are these effects at Mars?
I'm so interested in that. I started talking to people about it. That I'm really interested. I don't know. Yeah.
Strong.
Probably, yeah. Very good question. Dolan, yeah.
So when
So it's atomic. It's atomic and it's neutral.
Okay.
Yeah.
So
Now it's going to charge exchange, but it's basically with these high densities, it's stopped at the heliopause.
I see. And what sort of energies you would expect these particles to have?
So they depend on the velocity, right? They do increase to 40 kilometers because of the gravitational, right? Somebody has a question? Jeff.
Yeah. A critical thing of what you're doing is trying to search for an effective external force that would relate to the Earth's climate. And there's another force involved, namely ionization.
Mm-hmm.
At present, the two strongest sources of ionization from the interstellar medium are two stars, Epsilon CMA and Beta CMA, which are 120 parsecs away. But they're dominant in terms of producing ionization. It turns out that Mike Schall, former member of the Astrophysical Planetary Sciences Department, just wrote 3 papers, 2025, on what is the relative orbits of those two stars relative to the sun as they both move, all three move through space. And it turns out that 4.4 million years ago, those two stars were very close to the sun.
Yeah, we discussed that. That is interesting to.
Ionization is 100 or several hundred times larger than present. And cold clouds might not exist at that time. And there would be
Like we calculate, we need.
increase in pressure that would contract the heliosphere.
I think, like I said when we were talking, I think we need to realize calculate how much the increase in ramp pressure will be. The pressure from the charge exchange here is huge. I'll be interested to know the relative ratio of these pressures.
Any more questions from the audience?
No.
If not, please help me thank your speaker again. The white paper that you are referring